Chairman. Hello everyone. I am Shafiqul. So I came from this bottom corner part of Sweden, from a university called Making Institute of Technology. And this is a picture of the university, and the water that you see here is actually Baltic Sea. We are literally 2 meters away from the ocean, so it would be actually difficult to beat that. Yeah, as introduced, the topic of my talk is to look into the effect of stress triaxiality in knitting and failure strain in high density convective of HDP. It's a very simple study, so let's go into that, and maybe we can go into RD lunch. So this material high density polyethylene is used mostly to produce top portion of the packages, food packages. So this is injection molded. And historically, we know that this material is highly anisotropic, and being a viscoplastic material is highly dependent on the strain rate. And maybe it is not visible here, but if we put the engineering strain into the full curve, so we will see that the engineering strain for this material can go up to more than 10. So that means starting a test from here can go up to that much elongation before it fails or anything. So, so the problem description is, so we have to find the specimen that can induce different stress triaxiality. So that's one problem. This problem, as I'm saying, because this sort of specimen is already standard, but those are standard for metals. But when it comes to polymers, due to this high elongation, this is difficult to actually capture for different reasons. I will go into that soon. So first to get the specimen geometry, and then to calculate the triaxiality based on stress triaxiality based on the strain part. Stress triaxiality, as the name suggests, is a phenomenon that or that has to be calculated based on measured stress. But here we are trying to make an attempt to capture that or calculate that based on the strains. And the last problem, I mean, one of the presenters actually presented that it's kind of difficult to measure larger deformation using digital image correlation. So there are other ways, image processing software that could be used to measure that. So the last problem would be to how to solve that one. So let's go forward. So also this material, as you can see, so it starts making quite early when we have a stable making. And the local strain rate can be about 50 times higher than the global strain rate at the edge. And what happens there also, if you look here, that here we are using digital image correlation, so at the beginning it's possible to capture the strains locally, but as you go further and further, the stochastic patterns deform quite much, and it's difficult to actually follow. So that's why we have to actually also look into that and solve this problem to capture high deformations locally. And so now we have to design the specimen. As I said, that in the literature for metal, it's quite much available different shapes to induce different stress triaxiality. But this material being like a chewing-gum, that much flexible or deformable, we have to first solve the problem of capturing very high deformation. So the material model uses a simple one. This is isotropic. And then we have divided this hardening curve into 3 portions. This is fitted based on experimental data and by postcode, and this is a logistic, and finally a spline. And this curve is optimized against both the specimen curve from the tensor test using eyesight optimization. Once we have a trustable material, then we have optimized for this design of different geometry that can induce different stress triaxiality. And this is the final geometry, and then this is cut from this injection molded polymer plate. It's the same thing that happens at the top of the package, injection molded, and they are cut using this cutting die, and you can see the dimension and some of the other specification here. And we have cut the specimen both in meshing direction and cross direction. So meshing direction is, so this material is molten material is fed through this channel, and it flows to this direction, so we are calling it meshing direction. And maybe this is not very important, but this is the engineering stress strain curve for 3 different tests. So the first one, geometry maybe it's old, introducing a bit. So this one is HN, so we are calling that this is inertial tension, this is plane strain, and finally this is shear. So we are expecting this will produce different stress reactionality to the specimen. So this is the response in machine and cross direction. We can see they are different in 3 different geometries. So what is important then is to look at the strain path into major and minor stress. And we look at the strain path at the beginning, they behave as we expect. Maybe it's not obvious, but I will come to that point. And as we go larger and larger deformation, the strain path actually moves towards inertial tension, which is kind of a bit of vertical to the little inclination to the left. And as we know, like the stress reactionality is this ratio of mean stress by convex stress equivalent stress. Now this is the way usually you ideally would measure. It's difficult to measure the stress response directly from this test. So the alternative is to use theoretical yield function to calculate the stress reactionality based on the strain path. So we can see like von Mises prediction. We have these for cross direction, and this is for machine direction. And we also have a heat 48 prediction that's based you need some anisotropic parameter, namely Langford coefficient, and this you can see. So I can say like we have solved the first problem, to looking into stress reactionality dependence on the neck initiation. Now that would be a question, what is the initiation of neck? So for that one, I would say these are the stage. You can see the major, and in this case, for example, there's a minor stress distribution from BIC. So we have identified the neck initiation under a clear concentration of a band of a strains. And of course, the next thing would be like how to measure the strains when BIC cannot any longer track the pattern. So we use image macro. So basically you have 2 lines. And if you write a macro, that can track that line. And from there, you can basically get to the strain. So it is first have to be calibrated for how many pixels per length. That's probably standard. For example, here the width has been measured using. So finally, so these are the curve that we used to done using image processing software. So there is 2 ways we do image here. We also wrote a MATLAB code that actually tracks these lines, so grid lines. So these are the representative curve of the grid line strain ligament. So the end point of each curve actually gives the fracture strain or failure strain. As you can see, they are also pretty much the shape of the specimen dependent with that dependent on the stress reactionality. So here is a quick comparison of how the making strain and the fracture strain look for machine and cross direction. So something to look at, interesting that for shear strain, fracture and making strain for this material is quite close. That's one thing to take away, and also the making strain in machine direction is higher for this material, whereas the fracture strain or failure strain is lower. So some of the discussion, as I said, it's difficult to have the theoretical stress reactionality based on the specimen when we have this large deformation. This is difficult to get. And yeah, basically in conclusion, I would say the fractionality dependent material, this HDP is, and it's anisotropic in machine and cross reaction. We can use grid or some other sort of image processing software like image to capture these high local strains. And also, that's probably one of the important takeaway that as we go to higher deformation, the stress reactionality actually shifts from what theoretically expected towards uniaxial tension. So theoretically, in uniaxial tension, it should be 1/3. In plane strain, 0.57, and shear to be close to 0. And we have seen that this is not the case. We have seen that the stress reactionalities are in a narrow band for machine direction, and even a narrower band for cross direction. So I will conclude that it is dependent, but it's not highly dependent. Making insulation could be safe dependent, but for failure, it's quite insensitive to stress reaction, this particular material. So thank you very much.
Thank you. Any question? Okay, please. Yes.
So when you use the lines to measure engineer from the English tape, did you have the problem that even they got smudged a little bit, and because it's very large deformations, the sharp lines they would paint it?
Yeah, it's a bit difficult, but you can kind of track. We have also checked in one case with finite element simulation, of course. So it is difficult to, like here. So you can see like there's a smooth tracking. So what we have here, measure is the blue line here. So it's a smooth, it goes, but when you compare with finite element simulation now, we have to give that to anisotropy of the material, why they are different. But we get a smooth curve, but there are some error, of course, induced with that we haven't calculated how much back is. Yeah. But there are two methods that we have tried. One is image J, and of course you can write a MATLAB code and then calculate it for how many pixels for the initial length, and then just have a measurement of this one.
Thank you. Thank you all for being present in this section. Have a nice lunch and